Hi everyone. Thank you so much for joining me today. I hope you're having a great time at the conference. In today's session, we will be talking about extending your SQL applications to the edge using Azure SQL Edge. I'm Vasiya Krishnan, or Sia, and I work as a program manager for the Azure SQL Edge team in Microsoft. Before we get into the session, I would like to take a moment for everyone to explore everything PaaS has to offer, from training and networking to local user groups, free one-day local training events, and how to get involved as volunteers over here. Today, we'll be looking at the IoT landscape before delving into what Azure SQL Edge is. Post that, we will focus on how Raven has been using Azure SQL Edge to help its customers, and then finally, we will look at next steps. The Internet of Things, or IoT, refers to the billions of physical devices around the world that are now connected, constantly collecting and sharing data. Thanks to the arrival of cheap computer chips and the wireless networks, something as small as a button to something as large as an aeroplane can now be an IoT device. Gartner has also stated that by 2025, 75% of enterprise-generated data will be created and processed at the edge, up from less than 20% in 2018. IoT adoption continues to grow from 2019 into 2020, surging from 85% of companies using the technology to 91%. More companies view IoT as an important element of their business success and are happy with its performance. 90% of the organizations consider IoT as critical to the overall success of their business. Looking into the future, it's clear that IoT adoption will not slow down. 2 years from now, we see 95% of the organizations using IoT just as much or more than what they do today. Connecting up all of these different objects and adding sensors to them adds a level of digital intelligence to these devices. This opens up a wide range of IoT or edge scenarios across every major industry. IoT adoption is strong across industries. Organizations are adopting IoT as part of a broader cultural change to optimize their productivity and secure their environments. Within industries, IoT is used for efficiency in different ways. Could be production efficiency in manufacturing, remote health monitoring when it comes to healthcare, predictive maintenance in the aerospace domain, analysis and management of drone data when you think of defense, autonomous vehicles, point-of-sale devices in the financial sector, asset maintenance for energy, supply chain optimization in retail, and security solutions when it comes to smart buildings and homes. As you can see, IoT is all around us. By collecting and mining data generated by the devices at the network periphery, or edge, IoT holds the potential to increase business profits and improve customer lives. When it comes to the adoption of IoT, there are key challenges faced by the organizations. It broadly falls across infrastructure, network, and data. Challenges can further be divided across 5 buckets. First, connectivity. So dependence on an internet connection. Cloud-based solutions only work when an active internet connection is available. However, many IoT applications need to function offline. Autonomous vehicles, for example. These can be located in the remote parts of the earth where they have to make decisions based on the sensor data available to carry out next steps. One can't wait for an active internet connection to take decisions in these cases. Next is latency. The time delay between an action and its response is significant in a cloud application due to the round trip the data needs to take. A near real-time response is, however, critical for many IoT use cases. In case of a factory floor, decisions need to be taken spontaneously by machines on the assembly line. Latency in these cases will result in the loss of money for the customers. Next is security or privacy or data ownership. So there are added risks such as data breaches and or tampering when transferring data through the network as opposed to keeping or using the data directly at the source of its creation. Security is prevalent across all industry verticals, be it healthcare, financial services, or in security solutions for your houses. Next is bandwidth. The growth of data volumes and IoT devices exceeds the speed by which the broadband infrastructure can be extended. This puts a hard limit on the growth of applications depending on the cloud. What happens when you have to take a decision on a ship in remote locations of the planet like the middle of the ocean? Finally, high cloud costs. The more data is sent to the cloud and stored in the cloud, the more the cloud costs. Many companies find costs for cloud applications are higher than expected. To speed up the collection of data and reduce the risk of losing data, data must be collected, aggregated, synchronized, and processed close to the edge. The location is either on the device itself or on computers in the edge network. This is the point, the data management cycle, in which the database specifically built for the edge computing becomes important. You may be asking, why do I need a database at the edge? An edge database has specific features that make it easy for an application to focus on adding business value rather than implementing mechanical processes for integrating, collecting, and aggregating data in the edge, and then delivering the resulting data to the cloud or to your data centers. An edge database will automate these features even if your network is intermittent or slow. Azure SQL Edge has been developed by keeping these challenges in mind. Azure SQL Edge is an optimized relational data engine geared for IoT and IoT edge deployments. It provides the capabilities to create a high-performance data storage and processing layer for IoT applications and solutions. Azure SQL Edge is built on the latest versions of the SQL Server database engine, which provides industry-leading performance, security, and query processing capabilities. Since Azure SQL Edge is built on the same engine as SQL Server and Azure SQL, it provides the same Transact SQL or T-SQL programming surface area that makes development of applications or solutions easier and faster, and makes application portability between IoT edge devices, data centers, and the cloud straightforward. It is a fully containerized solution compatible with most Docker container engines. Azure SQL Edge can run on devices ranging from IoT devices to edge servers. However, to get ideal performance, your device should have a minimum of 2 cores and a few gigs of memory. It can run not only on your x64 architecture, that is Intel or AMD devices, but also on ARM64 devices such as your Raspberry Pi. It provides the same developer and tooling experience as that of SQL. Further, Azure SQL Edge supports connected, disconnected, and hybrid scenarios. In the connected scenario, Azure SQL Edge is available on the Azure Marketplace and can be deployed as a module for Azure IoT Edge. In the disconnected deployment, Azure SQL Edge container images can be pulled from the Docker Hub and deployed either as a standalone Docker container or on a Kubernetes cluster. While Azure SQL Edge is based off of the same Microsoft SQL engine and Azure SQL database that we all know, it brings with it a set of new features tailored to meet the demands of processing data at the edge. Let's take a look at a few of these features that are unique to Azure SQL Edge. Integration of data from the edge to cloud to data centers. When it comes to IoT, you would want long-term data storage capabilities for data analysis. Data can be moved through either the streaming layer or by batch processing to various Azure targets such as Azure SQL DB, Azure Cosmos DB, etc. Azure SQL Edge currently supports bidirectional data movement. Azure SQL Edge also has native integration with Azure products and services such as Azure IoT Edge and Azure Stack Edge. All of this enables 1. to use the whole Azure ecosystem to provide the best value to customers. Edge scenarios often require the flexibility to run on different devices and in different environments. We talk about the choice of platform from multiple perspectives. Expanded device architecture coverage to include ARM64 and x64 based architecture, choosing either a Windows or Linux as the host and using Kubernetes or Linux Docker containers to orchestrate your device infrastructure for better efficiency and automation. And finally, you can run SQL Edge in an offline or online deployment model to support various edge environments. With the increase in adoption of IoT and edge computing across industries, there is an increase in the number of devices and data generated from these devices. The increased volume of data and the number of devices contains endpoints, which pose a significant challenge in terms of security. Just like Microsoft SQL Server and Azure SQL, securing Azure SQL Edge deployments can be viewed as a series of steps involving 4 areas: the platform, authentication or authorization, objects, which is including the data objects, and applications that access the system. Some of the key features when it comes to security that Azure SQL Edge brings to the table are transparent data encryption and always encrypted capabilities, control accesses with role-based access control and attribute-based access control, and complying with security regulations with data classification. In terms of performance, we have also taken those that made a lot of sense when it comes to deploying SQL on containers, such as fast recovery, column store indexing, compression enabled by default. When it comes to IoT or edge deployments, capturing continuous streams of increasing amounts of data in real time and deriving valuable insights from it is a huge challenge. Azure SQL Edge provides built-in streaming capabilities for real-time analytics and complex event processing. The streaming capability is built using the same constructs as Azure Stream Analytics. The streaming engine for Azure SQL Edge is designed for low latency, resiliency, efficient use of bandwidth, and compliance. We currently support streaming through IoT Edge, IoT Hub, and Kafka clusters. We are constantly working on improving the source and target pairs that can be used for improving the streaming capabilities to and from SQL Edge. When it comes to time series data, it is twofold in Azure SQL Edge. We bring to you already existing time series capabilities found in Azure Stream Analytics, such as windowing, aggregation, and anomaly detection. We have also added capabilities to the SQL engine around time series specific functions and storage optimizations. Azure SQL Edge provides built-in machine learning and analytic capabilities by integrating the open format Onyx runtime. Onyx is Open Neural Network Exchange, which allows exchange of deep learning and neural network models between different frameworks. Onyx Runtime provides the flexibility to develop models in a language or tool of your choice, which can then be converted to Onyx format for execution within the SQL Edge. Let's look at some of the capabilities in action. First, we will look at data streaming from a Kafka server. In this case, we have machine telemetry data being sent to a Kafka server and then being read by the SQL Edge instance using streaming capabilities. Then we will perform anomaly detection and inferencing on that data. Here we have a connection to IoT device where all the demo modules are running. Kafka machine telemetry module is running on the device emitting data to the Kafka server. Let us run Docker logs output on the device to show the telemetry data being generated by the machine. Data is coming in every few seconds and there are about 10 different values that are generated, such as machine pressure, vibration, rotation, timestamp, etc. This is emitted by the module and that data is sent to the Kafka server. From the Kafka server, it is then read by the SQL module. What you see here is the statistics of the streaming module. What you see here is input events read from the Kafka server and output events written to SQL. We will talk about why there is a difference between the two shortly. So first of all, where is this statistics coming from? Let us look at this further. Here, I have created a streaming job with two different streaming queries. The first streaming query is creating a pseudo table from the inputs of the Kafka server, which does anomaly detection on that data, such as spike and dip and change point, to determine if there are anomalies in the data being captured. As you can see here, the accuracy rate is being kept at 95%. That is 95% accuracy in the anomalies detected. The limit duration is 30 seconds, so it will look at the last 30 seconds of data to see if there is any anomaly. So once I've identified the anomaly, the data is being written to the SQL table called machine anomalies. Raw data dump of the machine input data to the telemetry data, which is in the database. In short, the streaming job is taking data from the Kafka server. We are doing a windowed aggregation on the data. In this case, we are taking data coming in from the last 10 seconds using tumbling window function, doing anomaly detection during reading, and then dumping the raw data for future references. Let us now look at the output. First, we look at the data dump to see what data was captured. Then we run a similar query on the machine anomalies data to check for anomalies. We have identified some anomaly on the pressure data and no anomaly on the vibration data. Now we will look at a retention policy-based data cleanup demo. Collection and storage of data from connected IoT devices is important, but volume is huge and hence organizations should plan how much data they should retain. To address that scenario, we introduced a new feature called data retention policy. Once defined, then there is a background task that runs to clean up obsolete data. Setting retention on database is easy, as simple as an alter database command that we will see soon. So first, we create the database that we are going to use for data retention tests. Once the database has been created, we can set up data retention on it using alter database by using the set data retention as on or off. Now we will check if the data retention has been enabled or not. Run the query on sys.databases to see if column data retention enabled is set to 1 or not. Here we can see that it is set to 1, so data retention has been switched on. We will now create tables on the database. We are creating a table with a primary key clustered index, and if you look at the new syntax, we are enabling data deletion on the table with a retention period of 1 day. We were also specifying a filter column to help SQL understand if the data has become obsolete or not. Similarly, we are creating another table with an unique non-clustered index. Finally, we are creating a table with clustered column store index. If we run a query against sys.tables, you will find that we have new columns attached to it that defines the retention period and unit for each of the table that has been created. If you run a query against sys.columns, a new column has been added that tells you if a column is being used as a filter column for data deletion. We are now inserting data into the table. Table 1 with primary key clustered index table. We run checkpoint. So SQL has a simple data recovery model and we are planning to get rid of the logs. The checkpoint operation, as you see here, has written only 3 logs. Given we have set up data cleanup for 1 day, automatic cleanup will not run in this case. However, we can also do a manual cleanup for the purpose of this demo. So in this case, I am specifying the table on which manual cleanup should run, and this is an optional parameter which gives number of rows deleted as the output, that is the row count. So let us do the same thing on a column store index table. Insert 5 rows, that's what we are doing over here, and then we are going to rebuild the index. It will insert the rows and then compress it to a row group. And what we're going to do now is we can check this using sys.column store row groups, and you will see that the table has one compressed row group with 5 rows. Now let's add 5 new records for a total of 10 records. If you notice the output of the sys.column store row groups, it is 2 rows, one is open, one is compressed, and it has a total of 10 rows. Let us now run the manual cleanup task on this table. You will notice that 10 rows were cleaned up by the task. These are rows outside of the retention period. Now we run a query on the row groups. What we see here is that both have been deleted. If we do an alter index on all the data on this particular table, all of the data will then be deleted. To disable data retention by running the alter table command, again, this is what needs to be done. So in this demo, we saw how easy it is to set data retention on your tables. Customers have been transforming their businesses by using Azure SQL Edge. It has played a key role in improving factory efficiency, cost savings, improving processes, enhancing employee productivity, and accelerating delivery time. In short, Azure SQL Edge is enabling customers to move to Industry 4.0. In this section, we will take a look at how a couple of customers have transformed their businesses using Azure SQL Edge across connected, disconnected, and hybrid environments. Fugro. Fugro is a geointelligence provider that helps clients in the energy sector gain vital insights for planned marine projects. So these marine projects include offshore wind farms, etc. To support its clients in early project phases, Fugro sends a team of oceanographers, meteorologists, and hydrographers to collect environmental data such as water depth, wind waves, currents, and temperature. This marine geodata, which can be collected through sensors on Fugro vessels or ocean buoys, is vital to understanding how a structure such as a wind farm might behave in extreme climates. The offshore locations where Fugro collects data are often remote, and acquiring this data quickly and consistently was challenging Additionally, the quantity of data collected meant that analytics could be performed only on land, leaving Fugro unable to drive real-time insights. The company set out to fix these problems by moving analytics to the cloud and network edge. The Fugro team migrated its on-premise SQL Server environments to Microsoft Azure SQL database in the cloud. Then, Azure IoT Edge and Azure SQL Edge were deployed locally at the offshore project site on unmanned vessels. Thanks to Azure SQL Edge, time series data was now able to be ingested, queried, stored, and processed locally at the edge, saving the company significant time and costs associated with latency and bandwidth usage. The solution is so efficient that Fugro has reduced the time needed to process and deliver monthly data reports from offshore locations to client dashboards from 2 weeks to 8 minutes. With the help of IoT Edge and Azure SQL Edge, Fugro has improved the management and efficiency and resiliency of its solution infrastructure. Next, we have Achilles. Achilles is a leading plastic film manufacturer, and they were looking to improve their efficiency of the factory processes. That is around improving data analysis and standardizing employee production. Precision was something that was key to Achilles. They envisioned a system that gave crews access to the latest procedures for every production run. Using Azure SQL Edge, their IT team developed the Achilles shop floor data collection system, which provides crews with both an easily updated digital handbook for setting up every job and an on-site data collection mechanism. The company loads the digital handbooks on its Microsoft SQL Server, and the data is transmitted to handheld devices on the shop floor for up-to-the-minute guidance for every job. The crew uses Surface devices deployed on the shop floor that run the shop floor data collection system and Azure SQL Edge. So the devices display the digital handbooks for each job for easy reference, and crews update them periodically to document machine settings, which then syncs to the back on the company's on-premise SQL service. This production data, which once languished in a file cabinet, is now providing value. Along with providing guidance for the crews running the shop floor equipment, they're collecting values about shop floor conditions and machine settings that enhance quality. All of that feeds back into production design and manufacturing processes standards to give them control they have never had before. Next up is Raven. Life-saving hospital assets like ventilators and infusion pumps need to be mobile, but that mobility also means that devices can be difficult to find and then monitor them when you need it. This is a problem that has only been compounded by the COVID-19 pandemic, when the difference between good and poor asset tracking and management of particular assets in the hospital has truly become a matter of life and death. End-to-end data management and analysis to take the right decision was critical to Raven's customer. There are always challenges around ensuring data security at all points on the location. Some of the key outcomes were creating an automated reporting dashboard. These custom reports and dashboards automatically populated and are distributed to the relevant medical professionals and teams. These dashboards also led to better visibility of vital assets using real-time location to have full control of where and how ventilators are being used. This in turn led to better resource utilization. Further, there was always a scheduled asset maintenance that happens regularly, which can mean taking assets offline unnecessarily. Kind of leads to a shrunken pool of resources when you need them the most. Predicting when action is required means you can avoid unnecessary downtime. All of this, in the end, resulted in saving more lives. The IoT solution was designed primarily to obtain real-time visibility of ventilator location and utilization. The process began by identifying the critical data that needs to be collected to deliver the necessary goals. This included ventilator status and location and the medical bed status and location, and finally the schedule information. Azure SQL Edge was deployed as a part of Azure IoT PaaS platform on Raven certified Aero devices. As you can see here, some of the key features of Azure SQL Edge, that is built-in data streaming, time series capabilities, especially around anomaly detection and data aggregation, played a crucial role in real-time analysis of the ventilator information. Further, this data is also sent to the cloud, which powers Raven's dashboard and also aids in training of ML models that are deployed to the edge for ML inferencing. As Raven and Arrow say, investing in edge data services and platforms such as Azure SQL Edge creates the foundation for them to accelerate the delivery of new products and services to their clients. In this demo, we will see how Raven and Microsoft are working together to make healthcare IoT solutions more intelligent. For the purpose of this demo, I'll be assuming the role of a maintenance supervisor in the hospital. One of my key responsibilities is keeping our ventilators operational, a time-consuming and critical task in the age of COVID-19. What I have in front of me is Raven's customized dashboard. You can see the map of my hospital with the location of multiple ventilators across the buildings. If you look at the data closely, you will realize that it is often time series in nature. I'm tracking multiple data points for each of these ventilators, such as which room are they located in, what is the temperature of the device in there, battery state of the ventilator, and also battery of the RFID tracker on the ventilator. This was made possible by Azure SQL Edge that has been deployed on these devices. Native data streaming capabilities on Azure SQL Edge enables the devices deployed on the hospital floor to capture the real-time information from the ventilators. This helps me make most of my assets without having to spend my whole day conducting in-person checks. In addition to giving me visibility into imminent failures by collecting data over time and combining it with information like service records, I can start to build a proactive maintenance plan to minimize downtime and maximize quality of care. The data that I have been collecting at the edge is aggregated and sent to the cloud storage. In this case, it's an Azure SQL DB. This is possible because of the native data movement features supported in Azure SQL Edge. And by sharing the same data with my medical colleagues, they can remotely review and validate the device configuration irrespective of where they are located and take timely actions as needed for the patient's well-being. Let us now see how SQL Edge makes all of this possible. SQL Edge uses the same SQL engine as its data center-based counterparts, and as a result, I can use the tools I'm already familiar with, like SQL Server Management Studio, or in this case, Azure Data Studio. From Azure Data Studio, I can deploy SQL Edge directly to an existing container environment or an Azure IoT Edge device. Here, you can see the list of deployment targets available for deploying your Azure SQL Edge instance. As I mentioned, it could be a local container instance or a remote container instance, and at the same time, you can also deploy it as a part of your Azure IoT Hub, either a new one or an existing one, or on multiple devices on an Azure IoT Hub. In this case, I have already got my SQL Edge environment deployed, so let me connect to it. Just like any other SQL server, I can use a full range of T-SQL query syntax and get full intelligence support in this editor. From this query, you can see the raw data coming from the ventilator sensors across my hospital. The data frequency and volume means relaying this to the cloud for analysis isn't a good choice. Let's see how SQL Edge can make sense of the data locally. First, if you look closely, you'll notice some null values in the results of my last query. This can happen when the sensors fail to provide timely responses or unexpected values. Missing values makes time series analysis much more difficult. When dealing with time series data, it's often possible that this missing values for attributes occurs because of the nature of the data or because of interruptions in data collection, and that results in time gaps in the data set. So in Azure SQL Edge, a new syntax was added to tsql, that is the last value and the first value functions, which provide mechanisms to impute missing values based on the preceding or following values in the dataset respectively. The new syntax also adds ignore nulls or respect nulls clause to the last value and first value functions. So let's go ahead and run this query to see what happens by using the last value function. We're going to look at it as a form of a chart. So by using the last value function, what we see here is we have replaced the missing values with the most recent sensor reading, and this is just one of a number of time series capabilities in SQL Edge for local analytics. The next thing that we are going to see is around data retention. Collection and storage of data from connected IoT devices is important to drive and gain operational and business insights. However, given the volume of data originating from these devices, it becomes important for organizations to carefully plan the amount of data they want to retain and at what granularity. While retaining all the data at all granularity is desirable, it's not always practical. Additionally, the volume of data that can be retained is constrained by the amount of storage available on the IoT or edge devices. In Azure SQL Edge, database administrators can define data retention policy on a SQL Edge database and its underlying tables. Once the data retention policy is defined, a background system task will run to purge any obsolete or old data from the user tables. When managing real-time data, our edge device not only needs to be able to handle on-demand queries, but also perform analytics over the incoming stream of data in near real time. For example, here we can see a recent device anomaly where the temperature has increased unexpectedly. The maintenance team then receives a proactive notification of this issue. Azure SQL Edge provides a native implementation of data streaming capabilities called tSQL Stream. So it provides real-time data streaming, analytics, event processing to analyze and process high volumes of fast streaming data over multiple sources simultaneously. As with stream analytics, tSQL streaming recognizes patterns and relationships in information extracted from a number of IoT input sources. In this case, these are the ventilator devices that are there on the hospital floor. So you can use patterns to trigger actions and initiate workflows. So tSQL streaming works in exactly the same manner as Azure Stream Analytics. So a stream analytics job usually consists of a stream input, a stream output, and a stream query. So once that is done, we will be creating a streaming job in this case with anomaly detection built in, and we are using the anomaly detection spike and dip cast over here. And then post that, we will be starting the streaming job, and at the end, the result that we are going to see is what are the anomalies in respect to the temperature of the ventilator that is coming up on ventilator number 3. Let's go ahead and run this query now. So here you can see that we have a score that has been assigned to each of the
values that are coming out from the table. And also, we have also seen whether it is an anomaly or not. Given that we wrote a query that clearly picks out only those records that are above a temperature of 80 degrees, which means it's above, which means that we are considering it as an anomaly, you see that the score is 1 for every time the temperature is above 80 for this particular ventilator. While alerts and other key operational telemetry messages are best routed to the cloud via IoT Hub, bringing aggregated data sets up to the cloud can be more efficiently done through Azure SQL Data Sync. SQL Data Sync is a service built on Azure SQL Database that lets you synchronize the data you select bidirectionally across multiple databases in Azure SQL Database and SQL Server instances. Because SQL Edge is built on the latest version of the MySQL Server database engine, any data synchronization mechanism that's applicable to a SQL Server instance can be used to sync data to or from SQL Edge instance running on an Edge device. Setting up synchronization between a database in Azure SQL DB and a SQL Edge instance by using SQL Data Sync involves 3 key steps. First, you use the Azure portal to create a sync group. You can use a single hub database to create multiple sync groups to synchronize data from various SQL Edge instances to one or more databases in Azure SQL DB. For the purpose of this demo, we have already created a sync group called the DB sync group, and then those are what is called the sync members to the sync group. So set up the sync group to select the tables that will be a part of synchronization. So after you complete these steps, you will have a sync group that includes a database in Azure SQL Database and a SQL Edge instance. So when you look closely into the logs that is available over here, you will see that the sync has been happening successfully every couple of minutes with this database that is on the edge. What we'll be doing next is actually querying this cloud-based Azure SQL DB to see if the records have been syncing properly or not. So let's go to the query editor. We'll be logging into the SQL database using SQL Server authentication. Now we are into it. We'll just be looking at the maximum timestamp that is available on the database to see if the data sync has happened or not. So select max timestamp from real-time census record. Yep. So what we see over here is the maximum timestamp, which is 26th October, and that is the latest sync that has happened to the cloud target over here from the Edge table. So with this, it's clear that records from just a few seconds ago are already available for my cloud-based dashboards to visualize and carry out any kind of data analysis or ML training model, as we are going to see next, that is required to be deployed to the Edge for inferencing.
SQL Edge also has built-in ML capabilities with native support for running ONNX models inside the database. ONNX is Open Neural Network Exchange. And while Edge is the ideal place to run inferencing, mainly to avoid massive real-time data uploads, which is an expensive task, it is not the best place to build models. Once the data is in the cloud, as you can see here, I will be using Azure ML capabilities to train or retrain models that need to be deployed to the Edge for better inferencing and anomaly detection. So now let us spend the next few minutes trying to build a model that is going to be used to predict a device failure before it results in a complete service outage. First and foremost, I'm going to import the data set that I have sent to my Azure SQL DB Cloud Target. Once we fetch our data set, I'm going to be using AutoML to evaluate different model types. And as you can see here, I'm running 10 iterations. You can run more than 10 iterations in order to help you choose the best model out there. And what AutoML does is it helps us evaluate different model types and then It recommends the right one based on what is the best run fitted model that is suited for our data set. So once that is done, thanks to the native support for Onyx, the winning model can now be easily exported to Azure SQL Edge. Now let's see how the model that we have trained here can be used with Azure SQL Edge. So after loading it into the table, we can start referencing it. We can reference it using the native predict statement over here. So let's fetch the latest data for a particular ventilator and then use it to make a prediction on whether it's likely to be nearing a failure. Let me go ahead and run this query. So once that is done, you will see here that for the purpose of this demo, we are looking at 20 different ventilators, and out of which there is one ventilator which has label 1, meaning it is up for service sometime soon. In short, with SQL Edge, Raven was able to provide a more comprehensive asset management solution for their customers through richer historical and predictive analytics across the full real-time data and state only available on the edge. With its SQL Engine foundations, out-of-the-box support for streaming data and AI, and cloud integration through IoT Edge and SQL Data Sync, it is easier than ever to provide a fully featured intelligent data solution on the edge. To summarize, Azure SQL Edge simplifies edge architecture and IoT application development for customers by supplying a small footprint data engine that runs on a choice of platforms and delivers consistency in data tooling and security from edge to cloud. Powerful enough to run offline, but with the capability to connect seamlessly to a broader network of services, Azure SQL Edge includes built-in AI capabilities, support for time series data, and native data synchronization with SQL Server and other Azure services such as SQL Database. With Azure SQL Edge, customers have a small but powerful data engine that meets the challenges of IoT, which empowers businesses to use and analyze data collected at the network edge to save costs, drive innovation, improve safety, and gain competitive advantage. Azure SQL Edge brings to reality the goal of developing once and deploying anywhere across the cloud, data center, and the edge. Please head to aka.ms/SQL Edge to learn more about the product. You can try out Azure SQL Edge in the marketplace. If you would like to learn more about Azure SQL Edge in action, please head to our customer stories. Your feedback is very important to us, so please visit the session evaluation link in the left-hand side navigation bar to rate this session. And with that, thank you very much, and I hope you enjoyed this session.